Okay, we can start. So we are going now to discuss in detail the photodiode, once we have clarified these general definitions regarding light absorption processes in general. So let's have a look now in detail to the photodiode. So again, how do we make a photodiode? Again, like previously, the photodiode looks as a piece of semiconductor that is generally N. And there is a region that has been doped P+. And so this creates, if I put a contact here and the contact here, this is the contact to the P side and the contact to the N side. And so my photons are hitting this part, and they eventually will penetrate down to the active area that is represented by the region where the depletion region existing down there. And so this is the power of the photons that are hitting the device. So I will move this thing here just because I need the okay, so when the photodiode is in thermal equilibrium, this is a p-n junction. So in thermal equilibrium, the energy diagram should look like, as we know, something like this. This is the Fermi level, the conduction band, the valence band. Here is the N side, and here is the P side. So, and correspondingly, let me draw here the device like that. This is P, this is N. And imagine the device is in thermodynamic equilibrium. So, as you can see, there is no voltage applied across. So this means that if I wanted to attach a voltmeter, imagine, to these two ends and measure something, I would measure, if I attached a voltmeter to my p-n junction in thermodynamic equilibrium, how much would I measure? Zero. The built-in voltage is not accessible outside, it's internal, remember. So what is related to external is, it appears into some changes of the Fermi level. So this, here the Fermi level is flat. This means there is no voltage externally applied. So if I put a voltmeter there, I will measure zero. How much current will be flowing? Zero. That's what thermodynamic equilibrium means. Everything is not moving. Okay. So let us now imagine. So thermodynamic equilibrium also means, if you remember, go back to when we defined these things in semiconductor in chapter 2. Means also there is no light here, no light being shown on the semiconductor. So let us now imagine that still with no voltage applied, I start shining light on this. Now remember the story that this non-flat behavior of the conduction band is telling us that there is an internal or external? Internal. There is an internal electric field. So if I start shining light to this, what will happen is that photons will be absorbed, electron-hole pairs will be generated. Those photons, we've already anticipated that the active area is the depletion region. So those photons that hit the depletion region, and they have enough energy, always, remember, they will generate an electron-hole pair. This poor child will find itself in a region with an electric field, and so will move accordingly. So this electron finds itself in a region where there is this field, so this moves that way, and this moves the other way. Remember, in my mind, in this thought exercise, I still don't have any voltage applied. I'm trying just to measure it, if you like. So this means that these charges start to accumulate here. Imagine that you, obviously, while they accumulate, remember always that all the other processes that take place when we are out of equilibrium are still there. So this means that generation, recombination are still at play. Here we are heavily out of equilibrium, and we are generating carriers that shouldn't be there. What will dominate, generation or recombination? Recombination. They will recombine. These will tend to recombine. So even if I'm generating them, imagine a steady flow of light, I'm generating these holes and these electrons, they will also recombine. So there is an equilibrium there that will be established. If I keep increasing the flow of light, the photon flux, if I increase the photon flux, I will generate more and more. And so this means that eventually I have more and more charges, electrons here, and holes there, that although they are recombining as well, but overall, if I increase the photon flux, the photon flux, they will increase. Some are recombine, but if I'm generating more and more and more, they will start to increase as well, those that are here. Let's look now at this picture that we have on this diagram. So we had the internal electric field that is there because of the depletion layer. But now I've created here a negative charge, here a positive charge. This makes an electric field, again internal, that goes like that. So this means that while I shine light, the fact that these charges are, remember, the PN junction is not connected to anything. It's sitting there on its own, not connected to a circuit. I'm just shining light. I'm trying to understand what I'm doing here, what I'm causing. So we understand that there is an internal electric field, but the charge being separated also creates another electric field that is actually opposite to that. Now, here I've exaggerated this field, the arrow is too big. At maximum, this other field can be at maximum the same intensity as that. Because when this happens, when this other field, let's say, due to charge separation, counteracts effectively the internal one, the band diagram would look like that. When this field and this field become the same, the bands, the conduction band, there is no more field internally in the PN junction. So the bands are flat. I've counteracted completely the effect of the internal field. And we know the internal field is the one responsible for the non-flat shape of the conduction band or the valence band. So by counteracting that, that's what I should expect. Okay, but what does this picture? I'm going to touch now two things. So the first one, as I said, the maximum effect I should expect is that this field at maximum is the same as that. Why? If it was bigger, this means that overall there is an electric field going like that. This means that the shape of the band, the conduction, the valence band, should be with a slope like that. If that was to happen, electrons from here would flow there. And this is not allowed because this is not connected to anything, first of all. And second, eventually, this would reduce the charges there, reducing further the electric field. And so that's how we can realize that really the maximum field I could ever generate with this approach of light just going on the p-n junction is as much as the internal one, such to generate this picture. Did I manage to convince you? I can try to re-explain it. Huh? So I will come back to this in a moment. The second thing is, this was the Fermi level. This is the Fermi level on the n side, which we assume is at a reference potential. So what is happening here now is that, as I said, I'm doing nothing to the p-n junction in the sense that electrically I'm just measuring. The only thing I'm doing, I'm shining light. What I say is that now there is a potential being generated because there is now a non-leveled Fermi level. You see, the Fermi level here is there, and now here is here. How much is this? At maximum, like in this situation, how much do you think it should be? This is called QVBI. How much should be that? QVBI. So this voltage we've discovered. So what we discovered right now is that if I take a photodiode, a p-n junction, and you shine light, the junction is not connected to anything, you just shine light, you will generate a voltage at the two ends of it. Because the junction is not connected to anything, this voltage has a name. It's called open circuit voltage. Very, very original. So it's indicated as VOC. So what we just discovered is that VOC max, the maximum open circuit voltage of my p-n junction, is VBI. So it's positive, and this maximum is equal to VBI. So in general, will be between 0 and VBI. In this point. Very, very, very rapidly. So when there is no light, here there is an amount of charge that is the one due to the fact that the semiconductor is N. But if I start to shine light, there will be extra electrons that go there because of charge separation, extra holes. This extra charge will create an electric field that goes from in this direction. So it opposes that one. Now, an electric field that opposes that one, what it does is, as we said, the total electric field relates to the shape of the bands, to the slope. So if I'm effectively, by shining light, I'm effectively changing the intensity of the field, total field, which means I am reducing the slope. The more I shine light, the more this goes down. And so the slope becomes smaller and smaller, until eventually the conduction band, and so also the valence band, becomes completely flat. That is the moment when V at the ends is actually VBI. Now I wanted to convince you that I can't go further than that. So I want to convince you that this extra electric field at maximum can be equal to the internal one. So imagine that it was possible for this situation to happen. This is hypothetical. In this situation, what would happen is that these electrons see in front of them now, when the conduction band has this shape, remember that the electric field is related to the derivative of the band. So the derivative is positive, the total field now is like that. This means that these electrons feel a force of moving like that. So some of these electrons now that originated in the first place this situation are now the same, that will move in the other direction, and so will bring this back up, because you are, by removing charge from here, you are making the field smaller. So that's how it's a self-regulated process, let's put it this way. I hope I convinced you. Okay, so we introduced the concept of open circuit voltage here, and let's go to the next, the second part, which is now, I want to, so up until now we are contemplating the junction open circuited, and now we want to close the circuit. So imagine now to do this. You short circuit the PN junction, and you put an ammeter just to measure current. And we repeat the same experiment. The junction is there, initially in thermodynamic equilibrium, we start shining light. Because of the short between the two ends, let me draw now the energy diagram. How would you expect? There is a short between the P side and the N side. Short electrically means same voltage. So the P side and the N side have the same voltage. How do I draw the Fermi level? Flat. The Fermi level is flat. And so in this situation, the energy diagram looks like that. Still, if there is a photon reaching this point, this will generate an electron and a hole that gets separated, and now they recombine externally through the circuit. So this electron, imagine, goes out, hello, hole, and we recombine. So in this situation where the junction is short-circuited, the potential obviously is zero, but now there is a current. Is this current? These electrons, these holes that are separated due to the photons that are hitting the depletion region, and they generate a current. And this current, note that this current is flowing. You see, the holes are going in this direction. So the current is actually going like that now. Is opposite to the, normally until now, our formalism says we measure the current as positive when we go from P to N, okay? So this current is negative. So we call this current the short circuit current, also not very original. And just to emphasize the fact that it is negative, I will put a minus sign in front of it. So we define it like that, minus ISC, to emphasize that it's negative. It goes in opposite to this direction. So we have identified that in the photodiode, there are two important concepts, that is the open circuit voltage and the short circuit current. So concluding, we realize that the IV characteristic of my photodiode, in the dark, it's a pure PN junction. So in the dark is what we know, it's like that. But if we start to shine light, what we said is, when the voltage across the junction is zero, so when we are contemplating the short circuit situation and we shine light, we should see a negative current. When we are contemplating the open circuit situation, which means no current is flowing through the device, no current means we are moving on this axis, at most, the curve should reach VBI. So we will be somewhere here in these points. Do you think what I'm thinking? So this is for dark. Dark. When there is light, where could the curve be? Yes. So the higher is the photon flux. So sorry, I should use the black for the dark, and this is light. So the higher the photon flux, and this point here, well, any of these intersection on the y-axis, this is what defines minus ISC. And this is what we called, any of these points is what we called VOC, the open circuit voltage, that at best can be VBI. And so the final IV characteristic of my PN junction photodiode is I0 ta-da! So by few simple thought experiments, we came up with that and that. So I think that's quite nice. And we can also now, given that we understood how the sorry, what I wanted to tell you is, yeah, just in a moment. So from this characteristic, if I wanted to find, say, VOC from the characteristic, VOC would be the intersection of the characteristic with the y equals 0, so I equals 0. So I just need to set I equals 0. So I put all this quantity equal 0, and you can easily realize that this brings us to the conclusion that in this situation this becomes VOC, of course. And so if you reverse the equation, you get VOC equal KT over E ln 1 plus ISC over I0. Remember that this is minus, this quantity here is minus I0. So this is a nice little formula to tell you VOC given the characteristic. And obviously in the dark ISC is 0. There is no current generated due to the photons. There are no photons. So this becomes ln 1, which is 0. So VOC is 0 when there is no light, which is true. It has to go through the 0, 0, the characteristic. And furthermore, we can now find out a relation, as we did previously for the LED, also for light and absorption processes. And so here for the diode, we can look for a relation starting from the fundamental definition. We can look for a relation between eta E, the external quantum efficiency for light absorption, and the parameters of the photodiode of the device. So what do we need here? So eta E is the number of electrons and holes created, so that generate the current. So clearly this is related to ISC. This is ISC over E, divided by the number of photons that externally are hitting the device. And so this is as we've seen previously, is this quantity here, the photon flux times the active area of the device, that in this case is this area here. That we can write also in this way. ISC over E divided by, this quantity here can be written as the power of the photons over the energy of the photons. And so we have this nice, where am I going to write it? Here. So ISC. So we realize from this relation the relation existing between ISC and all these other quantities. So ISC can be written as E eta E phi of the photons time A, or also as E eta E time the power of the photon beam divided by the energy of the photons. So this is a nice formula together with this one that let you understand how ISC, for example, depends on the photon flux or the power of the beam. You can see, what do we understand from here? It's something quite interesting. ISC is proportional to the photon flux, or if you like, to the power of the beam that is hitting the device. And while instead, VOC has a nonlinear dependence on ISC, and so on the photon flux, because it's ln of that. Okay, so VOC, nonlinear dependence on the photon flux. ISC has a linear dependence on the photon flux. We like linear dependencies, especially for detectors. It's very important to have a linear dependence. So we definitely like ISC being linearly dependent on the photon flux. So we can also define another important quantity. I will do it up here. So we remember this relation, so I'll remove it. So that's quite easy to remember, is the p-n junctions IV characteristic minus ISC, so it's quite nice. So the other important quantity to remember is so we've looked at the external quantum efficiency, which is related to these quantities in this way. The other quantity that is very important for generally for photodetectors is the so-called responsivity R, which is the ratio. So who is responding to light is ISC. We've demonstrated it. When light is hitting the device, some ISC is generated. So it's the ratio between the light response, ISC, divided by the power of the source, the power of the beams, of the electrons, the photons that are hitting the device. And so this is clearly measured in amps per watt. And so by looking at this, this relation we've just realized that exists between ISC and all the rest, we can also write the responsivity as eta E over E of the photons. Now, I've written this thing on the wrong side of the board. I wanted to show you something, but probably I will just draw something here. So the responsivity, if you take a photodetector, a photodiode, and you look at it, the responsivity looks actually like this. If I plot here the energy of the photons, and here the responsivity of the device, looks like that. Has a peak, but then has a tail and falls off. So the reason why there are many things at play here. First of all, why the responsivity starts at TG? Yeah.
It only works
Yes, that's obviously the main reason. By looking also at this formula, let's trace back. The responsivity is related to eta E. Eta E, I've deleted it. Eta E, we said, depends on eta I. And eta I depends on alpha. Alpha, the absorption, can only start above EG. Okay, chain, it's a big chain, but that's the reason. So the responsivity has this behavior, the absorption is strong, very close to EG. So the responsivity is high, very close to EG. But then the responsivity falls. And the reason it falls is because, remember, eta E, in the end, depends on alpha. Alpha, if you allow me to plot it on this thing, alpha is something like this. Maybe even grows, probably grows, but it's something like that. While the responsivity goes down, and the reason is that in the responsivity there is actually, so eta E would stay constant, but it's then this inverse dependence on E of the photons that makes it drop. The idea here is that when you start exciting the semiconductor with very energetic photons, so in this region, for example, when you're using very energetic photons, those are not used efficiently. They still create just one electron-hole pair. They are excited very high in the band gap, in the conduction band or the valence band, but this energy then is lost through thermalization So there is a lot of heat also being generated through these processes. So these photons here are not very well used by the device because they have too much energy compared to the band gap of the device. Yeah. Okay. So to close on this thing on the photodiode, actually, on this thing general, photodiodes, there was now an important concept that I wanted to go through here. Important. I mean, it's a nice realization. I will briefly mention it because we need it for the solar cell that I want to do, but I will go in full detail later in the post-lecture video. But we can have a look at this idea on this plot. So this is about how we use photodiodes. There are two ways to operate them. The one is called photoconductive mode, and the other is called photovoltaic mode. So in the photoconductive mode, what we do is with a photodiode, what do we want to do is we shine some light, and this will cause some extra current to flow in a circuit. So let me do it here. So for the photoconductive mode, consider this circuit. So this is our potential V, and this is my output, let's say. There is a current here, and this is the output. So this is for the photoconductive mode, and the photovoltaic, the circuit would be simply so we have some photons here hitting the photodiode. So as you can see, the difference is that here there is a generator. I'm using an external generator to effectively reverse bias. So this junction here, this PN junction, is operated in reverse bias now. So this means that in this circuit, the photodiode is operating in this part. Why is being operated there? Because here you see that the characteristic is flat. There is an absolute one-to-one relation between the current flowing through the circuit and the photon flux. Is the best, the output of the circuit in terms of voltage is the best way to get a signal that in output through the current flowing through this resistor that is proportional to the photon flux, because I'm operating the PN junction in this region. In this case, instead, there is no voltage, no external source. So we've said when we operate a thing like that, we shine light, there will be some voltage generated. Now this is attached in a circuit, so there will be this voltage that we called VOC, if it was open circuit, okay? if it was open circuit. If we attach to the circuit, there will be some current now circulating. So in this case, there will be a certain voltage across the device, positive now, as I indicated here, with some current. But the current, remember, as we said previously in our initial analysis, the current now is because of the light and goes from N to P, as I indicated here. So the current is what we would call, on this plot, would be the negative part. It's negative, the current, in this situation. Or if I wanted to map, the current that is flowing here on the IV characteristic of the junction, I need to look at the negative side. So V is positive, but the current is flowing in the negative direction of the junction. So I'm looking at this side now. So I will go in detail on this later, but the thing to keep is photoconductive mode using an external generator. I'm working here. Photovoltaic mode, which is what we use in solar cells, we are working in this side. So this is nice because, as I said, there is a one-to-one relation to the amount of photons that are hitting the device. This is nice because there is no generator. Actually, that's why it's called photovoltaic mode, because we want to use it to generate electricity. Okay, and we will be working in this side of the plot. Okay, so let me leave the details of this, analyzing these two circuits for later. There is nothing really complicated. You just are doing the load line and see where it goes on the plot to get the full understanding of that. But there is really nothing more than that. So I just don't want to do it here, but I will leave it for later. So let's go to the solar cell. So the solar cell is a photodiode, a big photodiode, a very big one, just so that it can collect as much photons as possible. So the only difference between a photodiode and the solar cell is the amount of ISC that it can generate for the same photon flux. That's all. So everything we've said until now holds for the solar cell. And this operated in the photovoltaic mode, that is this one here. So for the solar cell, so this holds also for the solar cell, and we have our characteristic that was this one here, I0 e to the EV over KT minus 1 minus ISC. And we said previously ISC is related to eta, E, and so on and so forth, and C is the formula we found. So we are focusing now on this part, as we said. So in the solar cell, what we want to do is to maximize the amount of power that this device can give in output. So as we said, we are working here in this quadrant. So power, if I pick any point on here, power is given by, electrical power is given by the product between voltage and the current. I put the absolute value here just because the current, if you look at the formalism we've used, the current would be negative. But obviously the power here is positive, so that's why I'm putting here the absolute value. It's just a matter of formalism that I is negative according to this our notation. Okay, so power is this one. The power caused by this point I've chosen now on the IV characteristic of my solar cell. So what we want to do in the solar cell is to try to maximize this quantity, the power that is being generated because of photons hitting the solar cell. To try and, how do we maximize this? Well, we need to have the data for that specific, remember, each one of these lines correspond to a specific ISC, intensity of light being used. So I need to have the specific data points. So once I have the specific data points, I can do for each data point V time I, and then I can choose the one that maximize power maximum, let's say. Let's say that are these two, IM, VM. I need to literally pick each one of them, do the multiply V and I, and see in the end from the lot of data along this curve which is best. Will be somewhere where I've indicated there, along the knee. And so if we manage to find this, we can then define an important quantity for the solar cell, which is the fill factor. The fill factor is telling us how efficiently we are using the solar cell if it has this characteristic. And the fill factor is this optimum point divided by VOC of the solar cell, which is represented by this point, and ISC. I still use the absolute values just because every author, also in their books, depends how they define things. So just to make sure that we don't get in troubles, I put the absolute values on the currents always so that everything is positive. So the fill factor, a good fill factor for a solar cell is 0.7, 0.6, 0.7. What it represents is the ratio between the area represented by this square and this square, is the ratio between these two areas. That's what the fill factor is. And the other thing we can define, and probably here I have to stop. Do I have much to say now? Oh, we are nearly there. Okay. So the other thing I can define is the power conversion efficiency, eta P, defined as the maximum power output divided by the power of the solar input being that is hitting the device. So it's the power maximum, max, divided by the photon power, and so is Vm divided by which, if you like, you can use then this formula as well to put it in terms of FF, the fill factor. So this will be VOC, ISC over. Oh, in the LED, we demonstrated that eta P is kind of the same as eta E, the external quantum efficiency. So here too, because of ISC depends from eta E, as we saw previously, but VOC depends non-linearly from ISC. So in reality, eta P here has a dependency as well from eta E, but is a bit too complex to put it in an analytical way. So, but obviously there is a dependency. And and this power conversion efficiency goes from few percent to the record, maybe nowadays, maybe 20-something% for solar cells. And so at this point, I will probably have to stop. There was, I wanted to tell you something about an application, and then something about the solar spectrum and the piecewise equivalent circuit of the solar cell. So I will leave these things for the post-lecture video, and so tomorrow we will have the third tutorial on PN junctions. I will publish today the quizzes related to today's part. So we may do them immediately tomorrow, if we have time, of course. So it would be great if you can, have a glimpse of these quizzes that I will publish today so we can have a look at them tomorrow. Okay, thanks. See you tomorrow.